We will finish this lesson with one more example. Suppose we have the equation y prime equals the matrix 2, -1, 0, -1 times y. Again, we proceed by finding the eigenvalues. Here, the determinant of a minus lambda I is going to equal the determinant of the matrix 2 minus lambda, -1, 0, and -1 minus lambda. And so that's going to be 2 minus lambda times -1 minus lambda minus 0. And so we're going to set that equal to 0 and see that lambda is in fact -1 or 2. And we'll note that for this upper triangular matrix, our eigenvalues actually appeared on the diagonal. And this is a fact that you should have learned in linear algebra, and that is that the eigenvalues of a triangular matrix do appear on the diagonal. So it makes it easier to find the eigenvalues. Now, as for the eigenvectors, we can let lambda be -1, in which case we are trying to solve a plus I times v is equal to 0. And so that gives us the matrix 3, -1, 0, 0 if we plug in -1 for lambda. We're going to set that equal to 0 and solve. And so an eigenvector that would be natural to choose here would be to use 1 for the first component and 3 for the second component. Notice that this row times that column is going to equal 0. And then the second row times the column, of course, equals 0. For the other eigenvalue, lambda equals 2. And that's a minus 2I times v is equal to 0. Then when I plug in 2 for a minus lambda I, I'm going to get the matrix 0, -1, 0, 1. And set that equal to 0, 0. I'm going to reduce. So it's going to be 0, -1, 0, 0. Setting that equal to 0, 0. And so a natural eigenvector to pick here is that the first component can be anything, say 1, and then the second component absolutely has to be 0. Again, multiply this row times this column, you'll get 0, and then of course this row times that column will also be 0. So I have my 2 eigenvalues and my 2 eigenvectors. And so my general solution is going to be y of t is going to equal c1e to the -1 times t. That's the eigenvalue. The corresponding eigenvector is 1, 3. And then c2 times e to the 2t. That's my eigenvalue of 2 times the eigenvector of 1, 0. Okay, now that we've solved several different examples of linear systems of differential equations, let's see how the theory does connect to second-order differential equations. So we saw before that if we had a second-order differential equation, that we could convert that to a system of first-order differential equations by letting dx dt be the velocity, v. So essentially, we replaced x prime with v. And then we replaced x double prime with v prime, because that's the derivative of the velocity. And then we solved for v prime, which gave us negative c over a times x minus b over a times v. Now we can put that in matrix form. So d dt of x and v is going to be the matrix 0, 1, negative C over A, negative B over A, times the matrix, or times the vector xv. And so now we've put this second order linear constant coefficient differential equation in the form of a first order system of linear differential equations. Now, we'd like to solve this kind of using the same ideas with eigenvalues and eigenvectors. And the first question that we're going to ask is what is the characteristic polynomial for this matrix? Well, we need to take the determinant of that matrix. Maybe I'll call that matrix A. And we're going to take the determinant of A minus lambda I. So we're going to take the determinant of the matrix. That's a negative lambda, 1, negative C over A, and then negative B over A minus lambda. So when we take the determinant, that's going to be, let's see, negative lambda times negative B over A minus lambda, and then minus a negative C over A times 1. So that's actually going to be lambda squared plus B over A lambda plus C over A. And of course, we want to set that equal to 0. Now, what I'm going to do is I'm going to actually multiply this whole equation by A. And so we're going to get that 0 is equal to A lambda squared plus B lambda plus C. So my characteristic polynomial is A lambda squared plus B lambda plus C. But if you look back at my second order differential equation, if I approached solving that equation using the methods we had learned before, say guessing a solution of the form e to the lambda t, then the resulting characteristic polynomial was in fact A lambda squared plus B lambda plus C. And so I used the term characteristic polynomial corresponding to the second order differential equation. And that was exactly the right term to use because this characteristic polynomial is in fact the same as the characteristic polynomial that you get by looking at the first order system that corresponds to that second order differential equation. So the characteristic polynomials are in fact the same. The eigenvalues in this case are in fact going to be the same. And so now we've maybe solved that mystery of why I was double using the term characteristic polynomial.